Yes, good afternoon, everyone. We shall start our lab. Uh, See, in the previous lab, we have discussed uh, this one, which were the 8 is to 1 multiplexer IC that uses EVM technique, entered variable map technique. And till now, we have discussed the 5 experiments. Today, we'll discuss this binary to gray and the asynchronous counter. These two experiments we will discuss. Uh, First, we'll start with this. The easiest experiment out of this 9 will be this one, the seventh experiment. Easiest of easiest. You can close your eyes and you can do this experiment. Design and implement code converter using binary to gray, gray to binary using basic gates. See what actually this experiment is. You know the binary code. Everyone know the binary code. What is binary code? A number 10. If I say number 10, in terms of ones and zeros, you are going to write number 10 means 1, 0, 1, 0. This is a binary representation. This is the most widely used coding. Binary coding, it is the most widely used. Even the computers can understand this. Many of the devices can and are going electronic devices will understand this binary codes. These codes are they right binary. It should be converted to a gray code. There is another system called gray code that is also been written using zeros and ones itself. But way of converting it, writing it is different. The 9 in binary is 1001. But in case of gray code, it is different. Both binary and gray code we are going to write using ones and zeros itself. But the way of converting it from decimal to the binary and from decimal to the gray, it is different. What actually here the problem statement is, you have to show a circuit where you give a binary input, the output from that circuit should be gray code. Or you give a input gray code, the output from that circuit should be the binary code. For all these things, you have to use a simple basic gates, AND gate, OR gate, NOT gate. All these gates you have to use and design. It is not decimal to binary or decimal to gray. It is from binary to gray or gray to binary. The circuit finally it is using the basic gates. Where actually binary codes are used? Everywhere they are going to use in your from normal computer to so many electronic devices, small devices. Everywhere this binary system is being used. Where actually the gray codes are used? Even the gray codes are used in optimizing the error correction or spurious output, some wrong outputs it is going to generate, where some electromagnetic switches will be there. Electromagnetic switches means due to some current, there will be a change from input to means from on to off. With the electromagnetic, they are going to call it as electromagnetic switches. There is a chances of giving the wrong outputs. They are called as spurious outputs. There they are going to use this gray codes. And in the digital communication, they use this gray codes. In the old, the terrestrial TVs or some cable systems, there they are going to use this gray codes. Means those systems will understand gray code. Your computer can understand gray code? No, it will understand binary. In the same way, that system will understand gray code. That's all. There are uses of gray codes in the digital communication or to prevent the spurious outputs in the electromagnetic switches in those places where they use these gray codes. and you have understood where actually binary codes are used, because in real time, in the real world, everywhere you are seeing this binary code. Okay, that is what the background about the binary and the gray code. You actually know the binary code. If I say some number, you will quickly divide it by 2 and you are going to convert it into binary code. Now, to convert from binary to gray code, there is some formula. Hmm? If you just remember that formula, it is enough. See, here in this experiment, we are using 4 bits. 4-bit representation. 4 bits binary code. What is the 4 bits gray code? Not less than that, not greater than that. But the formula here, what we show, it is for n bits. N bits means if I say some number for 10 digits, 10 bits binary code, this formula should work for to convert it into 10 bits gray code. If I say some 100 bits binary code, and you can convert it into 100 bits gray code. That is how the formula. This formula is not limited to only 4 bits, but actually on the hardware or what you are going to show, the output is for 4 bits. Next, binary to gray code. First, we'll see binary to gray code. If you check the MSB, MSB means the left hand side, first bit, left hand side, most significant bit of the binary code and the gray codes are same. They are same. For next bits, for a next n bits, the mth bit of a gray code will be BM XOR, you remember this, GM equals BM XOR operation, BM plus 1. That bit, binary, that bit with the next bit. With the example, we'll see. See, for any bits, the formula is this. G1 equals B1 XOR B2. G2 equals B2 XOR B3. G3 equals B3 XOR B4. That's all. We'll see one example. Binary to gray code first. Don't worry about this gray to binary. First, we'll see this binary to gray. See, this is a binary code. Don't see the right hand side. How to write the table first? See, if you don't write the truth table, you cannot write the circuit. If you don't write the truth table, you cannot write the equation. If you don't write the truth table, you cannot directly pass these values into the K-map. For that reason, first you have to write the truth table. First, we are discussing binary code to the gray code.
Sir,
Uh,
screen not shared, sir.
okay. Okay. Have you heard of, you got the background about the binary to gray, right?
Yes, sir.
Okay. Okay, now we'll go to the, see this formula. Binary to gray code. See this binary to gray code, the MSB bit of the binary code and the gray code will be same. Just see only this formula first. Don't worry about the second one. For next bits, it will be the XOR of binary, see like this, G3. If I take the example G3, B3 XOR B4. If I take some G2, means the gray code second bit, then binary second bit XOR binary third bit. If I say some G10 in the gray code 10th bit, then how will get the 10th bit? Binary 10th bit XOR binary 11th bit. As simple as that. This is the formula to convert binary to gray code. See now, the truth table. I think you have understood what is the use of why you have to write the truth table. In all the digital experiments, you should know the truth table. If you know the truth table, then only you can write the equation. For simplified equation, you have to enter into the K-map. Once you have a simplified equation, you can write a circuit and then you can demonstrate it on the hardware. Then you can demonstrate on the hardware. As I already said, we are going to show it for 4 bits. 4-bit means what will be the minimum value? 0. Maximum value 15. Don't worry about these values. The right hand side output, you know how to write the binary 15 inputs. 8 zeros, 8 ones, 4 zeros, 4 ones, 4 zeros, 4 ones, 2 zeros, 2 ones, 2 0, 2 ones, 2 0, 2 ones, and 0 1 0 1 0 1. These 16 values you can easily write. In order to write for the gray code, as I already said, if it is 4 bits means directly you copy B3 to G3. MSB will be same. Don't apply the formula for this bit, because if you apply the formula G3 equals B3 XOR B4, B4 is not there. That is why directly you copy the first bit MSB directly to the gray code. I think it is clear how to write G3. Next, to write G2, the formula, simple formula is B2 XOR B3. What is XOR? If the bits are same, 0, 0, 0, 0, 1, 1, 0, 0, 1 or 1, 0, it will be 1. That is an XOR. That truth table, I think you already know. Now, see here, 0, 0, XOR operation, the answer will be 0. G2 equals B2 XOR B3. G1 equals B1 XOR B2. G0 equals B0 XOR B1. See here, in the second case, 1 XOR 0. That is why you have seen 1 year. In that way, you can easily fill this truth table. Or else the students have their own logic, or own ideas, or they have their separate way to remember this truth table. They will even by heart this, or some ways are there. Means 8 zeros, 8 ones. Instead of applying the formula, what they will do is, since already the MSB is same, easily they will write this. After that, 4 zeros, 4 ones, 4 ones, 4 zeros. Just a reverse of it. Then 2 zeros, 2 ones, 2 ones, 2 zeros, 2 zeros, 2 ones, 2 ones, 2 zeros, 0 1 1 0, 0 1 1 0. In that way they will remember. But that is another blind way of remembering that. But when it will be correct, when it will does not go wrong is the, if you remember the formula. That's all. Even you can cross check afterwards like that. Another the blind way. So here, what is the formula for G naught? How you will get this? B naught XOR B1. The same location, the same index, G naught equals B naught, the same index with the next index, B naught plus B1. I think in that way you can fill this truth table. After this, for each bit, G naught, G1, G2, G3, we have entered those values, all these values from here till here, all the 15 values we have entered inside this K map. Here there is an quad, sorry, how much? 8 values, octet. When there is a octet, the formula we have got is G3 equals B2 XOR B3. Since we have simplified the equation and we have got the equation B2 XOR B3, I think I'll not discuss about how to simplify the K map. And how we have written this is all those 15 values of the G3. This is the K map of the G3. This bit. We should write the K map for G2. We should write the K map of G1. We should write the K map of G0. 4 K maps. In 4 K maps, 4 equations you are going to get. Then 4 equations, we are going to write it, the equation for that. See, we have got the equation like this. As I already said, since the problem statement is using the basic gates, but when this is the limitations of the hardwares in the lab. See, since we have parallelly, we are going to do so many, almost 20 students is going to do this experiment. We'll get a shortage of instruments. That is why what we have done is, instead of using the basic gates, we have made it to using we have made to use the XOR gate. Since the equation contains XOR, since you can write even this, say, even you can write using this basic gates. How? G1 equals B1 XOR B2, or this is equivalent to B1 B2 negation plus B2 B1 negation. You can write like that. In that way, if you write, you have to use AND gate, OR gate, and NOT gate. Instead of that, we have directly written, we have represented with the XOR. The same case. Instead of this XOR, you can write it as with the and OR and NOT. How? B0 B1 negation plus B0 negation into B1. In the XOR equation, you already know. A XOR B equals A B bar plus A bar B. In that way, you can represent. In order to simplify this equation, say with the just 3 XOR gates, you can complete the work. How we are going to get G3? Directly input will be connected to the output. On the trainer kit, you are going to directly connect input to the output. Whatever, if you give 0, you will get output as 0. If you give 1, you are going to get the output as 1. If you want G2, what you should do? You want to do the XOR operation. Therefore, we will take XOR gate. 7486 is the IC. That IC, we are going to take, and we are going to connect one input pin B3 to first pin and B2 to the second pin, the third pin to the output. Next, then second IC will be there. How we are going to get G1? B2 XOR B1. The B2 input, you are going to give it to the second XOR gate, and another input to a second XOR gate, you will get G1. In the same way for B0. Directly you give 4 bits, you will get the 4 bits as an output. This is binary to gray. Very simple. What I have observed from past 3 to 4 years is, if they get this experiment, they are going to complete within half an hour all the writing, procedure, components, everything, and completing the experiment within half an hour to 45 minutes. They'll complete this experiment. Do you have any doubts in this binary to gray? Then we'll go to gray code to binary. Anyone? If you have any doubts, you can ask. No doubts? Okay. If you don't have any doubts, then we'll go to the gray code to binary. See, the next formula you have to remember is, it is almost the same, a slight difference is there. Gray code to binary, in that case, the MSB bit of gray code and binary code will be same. That is same, because in case of binary to gray code, That is the same case. In the same way, by gray to binary, MSB of the gray code and the binary code will be same. But what about the next bits? For next n bits, if BM equals GM XOR GM plus 1 XOR up to the MSB. This is somewhat confusing. We'll see with the example. Now, to write gray code to binary code, in order to convert from gray code to binary code, you have to write first the gray code table. How to remember these values 0 to 15? You can see the previous table. You can see the previous table, or I have told, as I already said, a blind method, 8 zeros, 8 ones, 4 zeros, 4 ones, 4 ones, 4 zeros, 2 zeros, 2 ones, 2 ones, 2 zeros, 2 zeros, 2 ones, 2 ones, 2 zeros. That blind way you can follow. Right hand side, how to fill the output. Input is clear now. How to write the output. In order to write the output binary code, the formula for how you to write B3 is, it is same. G3. Write all the 8 zeros, 8 ones. In order to write for B2, G2 XOR G3. Simple, it is almost the same. For B1, G1 XOR G2 XOR G3. What about for B0? G0 XOR G1 XOR G2 XOR G3. All the higher order bits you have to XOR. From where you start, from that index, you have to XOR all the higher order index. That is what the difference from gray code to the binary code. What about the B0 formula? B0 equals G0 XOR G1 XOR G2 XOR G3. What about the formula for B1? G1 XOR G2 XOR G3. For B2, G0 XOR G3. What about B3? G3. In this way, you can write it for any number of bits. But here we have restricted only for 4 bits. In the lab, here it is going to be restricted for 4 bits. You can write for any number of the bits. I think this formula is clear now. The same 8 values, we have moved to the K map and we have got this equation. What about B3? It is G2 XOR G3. What about B1? G1 XOR G2 XOR G3. What about, here you can see, G3 equals B3. Sorry, B3 equals G3. What about B2? You will have to XOR G2 XOR G3. What about B1? You have to XOR these three, G3, G2, G1. There will be in the market, you don't get 3 input XOR gate. You don't get 3 input XOR gate. That is why what we do is we get the output of G3, G2 XOR. Output pin will be there, right? Third pin. That pin will be given as an input to the second XOR gate. In that case, you will get the XOR operation of G2, G3. If you add it with the G1, then you will get the output of B1. In the same way, if you get the output of this XOR gate, this is the result of G1 XOR G2 XOR G3. Directly, if you XOR with the G0, you will get B0. It is a simple logic to simplify the number of XOR gates. If you don't use this simple logic, there will be more number of circuits. That is why this logic, why the output will be connected as an input is Because of that reason, B1 equals G1 XOR G2 XOR G3. G2 XOR G3 output is already available here. The same output, one pin you connect it to the output pin, another you connect it to the input to the next XOR gate. Very simple. And in the same way for G0, connect the output of the second XOR gate to the third XOR, and one more is from the input pin. You will get B0. It is as simple as that. In this way, you can give 4 bits gray code, you will get 4 bits binary code. If you enter 4 bits gray code, you will get 4 bits binary code. Finally, on the trainer kit, you have to give this input and you have to show this output. All the 16 combinations you have to give an input, and 16 combinations you have to give a output. It is as simple as that. That is why I said, since we are using XOR gate, the life is become very simple using this in this experiment. If you use the basic gates for this, the number of the circuits will become very big on the trainer kit. That is why we have reduced it and we have used the XOR gate. But you should know, you should not learn with the blind method, the gray code. I think you can easily write the binary code. I know you will going to write, but for this one, which one? For gray code, you have to remember with the formula itself, because sometimes in the as a external, as an when they come for Viva, they will give you 10 bits, 10-bit binary, and they will ask you to write the 10-bit gray code of that. In that case, how you can remember? In that case, you, if you know the formula, you can easily write. Whether it is binary to gray or gray to binary, if you know this formula, you can easily write. If you have any doubts, you can ask now. Any doubts in binary to gray or gray to binary? Is everyone writing the record? Abhishri, Abhishri GL, are you there?
Yes, sir.
Have you written the record?
Sir, I'm still writing it.
Still writing.
Yes.
Why? We have given enough time, right?
Yes, sir.
Since we are not going to ask and you are not coming to college, you are taking so much time. Is it so?
No, sir, not like that.
How many experiments you have written?
2.
2. Okay, good. Aishwarya P.
Yes, sir.
Have you written the record?
One experiment ಅಷ್ಟೇ sir.
Huh?
One experiment, first experiment.
First experiment ಬರ್ದಿದ್ದೀರಾ?
Sir, ಅದು ಅನ್ಲಾಗ್
ಅನ್ಲಾಗ್ ಒಂದು ಬರ್ದಿದ್ದೀರಾ?
ಎಸ್ ಸರ್.
ನೀವು ಹಿಂಗೆ ಬಿಡ್ತಾ ಹೋದ್ರೆ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ಸ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ, ಆಮೇಲೆ ಎಲ್ಲ ಒಂದೇ ದಿವಸ ಬರ್ದ್ಬಿಡ್ತೀರಾ? ಇವತ್ತೆಲ್ಲರ ಕಂಪ್ಲೀಟ್ ಮಾಡಿದ್ರೆ ಆ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ನೀವು ಬರ್ದಿರ್ಬೇಕು, ಅಲ್ಲಿವರೆಗೂ ಬರ್ದಿರ್ಬೇಕು.
ಓಕೆ
ಸರ್, ಎನಿ ಡೇ ಐ ಕ್ಯಾನ್ ಆಸ್ಕ್ ಯು ಟು ಸೆಂಡ್ ದ ಸ್ನ್ಯಾಪ್ಶಾಟ್ ಆಫ್ ದಿ ರೆಕಾರ್ಡ್. In that case, in that date, you should be ready. Then you cannot take the excuse on that day. We are going to consider based on that also. We are going to give you the lab marks. ನೀವ್ ಹೆಂಗಿದ್ರು ಕೇಳಲ್ಲ ಅನ್ಬಿಟ್ಟು ನೀವು ಬರ್ದಿಲ್ಲ ಅಂತ ಅಂದ್ರೆ ನಾವು ಯಾವ ತರ ಇವ್ಯಾಲ್ಯೂಯೇಟ್ ಮಾಡ್ಬೇಕಾಗತ್ತೆ. ಇವ್ಯಾಲ್ಯೂಯೇಷನ್ಗೆ ಅದರ ಒಂದು ಪ್ಯಾರಾಮೀಟರ್ಸ್ ಇಟ್ಕೊಂಡಿರ್ತೀವಿ. ಆ ಪ್ಯಾರಾಮೀಟರ್ಸ್ ಅಲ್ಲಿ ಈ ರೆಕಾರ್ಡ್ ಬರೆಯೋದು ಒಂದಿರುತ್ತೆ. ಆ ಪ್ಯಾರಾಮೀಟರ್ ನೀವು ಆ ಕ್ರೈಟೀರಿಯಾ ಬರ್ದಿಲ್ಲ ಅಂದ್ರೆ ಅದ್ರ ಪರ್ಸೆಂಟೇಜ್ ಆಫ್ ಮಾರ್ಕ್ಸ್ ನ ನಾವು ರಿಮೂವ್ ಮಾಡ್ಲೇಬೇಕಾಗತ್ತೆ. ಹಂಗಾಗಿ ನೀವು ಎನಿ ಟೈಮ್ ಆ ಲ್ಯಾಬ್ ಆಗಿದೆ, ಆ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಆಗಿದೆ ಅಂದ್ರೆ ನೀವು ಅದನ್ನ ಕಂಪ್ಲೀಟ್ ಮಾಡಿರ್ಬೇಕು. ಇಸ್ ಇಟ್ ಕ್ಲಿಯರ್? ಯು ಪ್ಲೀಸ್ ಇನ್ಫಾರ್ಮ್ ಟು ಅದರ್ಸ್ ಆಲ್ಸೋ. Chinmay? Chinmay, are you there?
Yes, sir. Sir.
Have you written the record?
Till third experiment I have written, sir. I have to go through fourth and fifth.
Okay. Okay, we'll disconnect now because the Zoom is going to, the time is limited for 40 minutes. And after 5 minutes, once again, I'll send a message in the group, and then once again you can join and you will start the next experiment. Okay? Now we are going to disconnect, and after 5 minutes, we'll join once again.